Life seems necessarily to involve plans or models. Every living organism has in its DNA a plan of itself, or rather a plan to construct a copy of itself. Each organism also seems to have at least some model, however minimal, of how to survive within its environment. So, the science of living systems cannot be reduced to physics and chemistry, which are sciences of matter. Living science must also operate at the logical or symbolic level, the level of meaningful relations. The computer revolution has made it feasible to study this logical or symbolic level of life. In fact, questions about the logic of life were posed almost as soon as the first computer was constructed. John von Neumann, a Hungarian mathematician who immigrated to the United States, helped design the first computers in the 1940s. At that time, he established the principle of separating the operating instructions, or software, from the machine itself. This lets the computer become a general-purpose machine, carrying out any set of instructions entered into it. As Christopher Langton says,
"The logical form of a machine was separated from its material basis of construction, and it was found that machineness was a property of the former, not of the latter." Of course, the principal assumption made in artificial life is that the logical form of an organism can be separated from its material basis of construction, and that aliveness will be found to be a property of the logical form, not of the material basis. Today, the formal equivalent of a machine is an algorithm, which is the logic or program underlying the dynamics of an automaton, regardless of the details of its material construction. We now have many formal methods for the specification and operation of abstract machines, such as programming languages, formal language theory, automata theory, recursive function theory, and so on. Many of these have been shown to be logically equivalent.
in raising questions about the nature of life, von Neumann asked, what kind of logical structure or organization enables life to reproduce itself? Artificial life researchers Pablo Tamayo and Hyman Hartman described von Neumann's approach.
The first attempt in modern times to model self-replication by artificial life was made by von Neumann. He had just invented the internally programmable computer by implementing Turing's universal computing machine. This inspired him to found a new field of automata studies. One of the first problems which he attacked was the ability of a machine to reproduce itself. The question reduced itself to whether a universal constructing machine was a logical possibility. He answered this question in the affirmative by separating the description of the machine from the constructing functions. The remarkable aspect of his construction is that it was realized in the findings of molecular biology in the years following his death.
Von Neumann's work on self-replication produced an idea that originally was just a byproduct of other work, but it later became a very important concept. Cellular automata are extremely simple and purely abstract computer games that can be used to model life in a particular way. Computers can repeatedly apply the rules of a particular cellular automaton and thereby grow it. The result is compared to what's found in the real world, so the automaton and its rules can be evaluated to see whether they approximate the rules followed by some living organisms. Tamayo and Hartman describe the impact of cellular automata on the sciences.
At the suggestion of Stanislav Ulam, von Neumann went on to invent cellular automata in order to further implement his self-reproducing automaton. Since that time, we have seen an enormous expansion of this field. The cellular automata, born in the attempt to understand perhaps the origin of life, are now modeling hydrodynamics and reaction diffusion systems. In fact, we have here a case of artificial life modeling a large and growing area of physics and chemistry.
Cellular automata have proven to be one of the most useful tools for investigating general questions about self-organization and the logical nature of life. One of the most useful and widely studied automata is John Conway's game called Life, invented in 1970. Gerard Vishniak explains the game, which is played on a checkerboard of square cells on a computer screen.
It describes multiplication and extinction in a population of cells. The rule is the following. A live cell remains on in the next generation if there are presently 2 or 3 other live cells among its 8 neighbors. It will die by isolation if it is surrounded by 0 or 1 live cell, and by overcrowding if more than 3 neighboring sites are occupied. An empty or dead cell will come to life in the next time step if it is surrounded by exactly 3 live parents. In Conway's universe, only ménage à trois procreate. A remarkable feature of this computer game called Life is the emergence of ordered patterns out of a disordered initial condition, the primeval soup, thus escaping the tyranny of the second law of thermodynamics.
This automaton has achieved considerable popularity as a computer game, but while its rules are simple, it holds deep lessons for those who pay attention. Vishniak quotes the physicist Roger Penrose, who sees the modeling power of cellular automata as a metaphor for the universe.
It is hard to resist the tempting argument that the game offers a model for our universe, itself presumably governed by rules of the utmost simplicity, yet exhibiting the richness and complexity we observe around us, especially in living things.
Conway's game of Life has been shown to be formally equivalent to a system invented by Alan Turing called the Turing machine. Both are capable of universal computation. This means that the game of Life can represent any possible set of operations on any possible computer. It can generate structures of any degree of complexity, and it can produce order at any scale. Chris Langton is one of the leaders in cellular automata research. He shows that cellular automata are brilliant models for describing self-organization, but they generate highly complex structures only under very special conditions. Most cellular automata produce either simple forms, like simple geometrical patterns, or chaotic forms, which lack large-scale structure. Only at the borderline between the two kinds of behavior can truly complex organizations appear, with structures on all scales. These are the organizations that have fractal properties. Complex structure thus seems to represent a sort of balancing act between order and chaos. Langton describes it like this.
We find that there exists an upper limit as well as a lower limit on the complexity of a system if the process of synthesis is to be non-degenerative, constructive, or open-ended. We also find that these upper and lower bounds seem to be fairly close together and appear to be located in the vicinity of a phase transition.
An example of a phase transition occurs when ice changes to water. In ice, the molecules of water form highly ordered crystals. In liquid water, the molecules are arranged in a random way. Langton continues,
we find that one observes a phase transition between highly ordered and highly disordered dynamics, analogous to the phase transition between the solid and fluid states of matter. Most importantly, we observe that cellular automata in the transition region have the greatest potential for the support of information storage, transmission, and modification, and therefore for the emergence of computation.